So we are welcoming here Salt Kira. He's assistant professor at the Georgia Institute of Technology. Salt is also the lead of the Robotic Perception and Learning Lab. He received his PhD in 2010 with Professor Ron Arkin, who's a pioneer in robotics. What I find really interesting is that his research is combining application for robotics, different types of perception, including vision, but also 3D point clouds, with fundamental, I would say, research questions related to also machine learning, for example, regarding auto distribution, sample robustness, and domain adaptation and semi-supervised learning. So I think a perfect fit for our workshop over here. He's a senior program chair for ICHCAI and area chair for NeurIPS 2020 and ICLEAR 2021. And I think his work is published in its oral presentation at ICV, CVPR, IROS, and AAAI. So the slide is also on, I see now. So with no further ado, Salt, we will make you co-host.
Yeah, okay, great, thank you. Yeah, I'd like to thank the organizers for inviting me. This is a great workshop. So today I'm going to be talking about leveraging single and cross-modal unlabeled data for learning with unlimited or with limited labels. So really what we're trying to do is push the boundaries on how to learn models for perception that are useful for applications such as autonomous vehicles with much less labeled data, or leveraging a lot of the advances that we have in autonomous vehicles such as multimodal inputs and so on. So the past few years have seen a great amount of progress in learning from reduced amount of labeled data. Prior to that, deep learning has been used widely and has achieved a lot of successes, but has really always kind of required lots of data. And so in the past year or so, there's been a lot of work that's great from industry as well as academia, looking at all these machine learning settings that go beyond supervised learning, which is where we've had a lot of successes. So this includes, zero shot and few shot learning, where you have only a few examples, semi-supervised learning, where you have a mix of labeled and unlabeled data, self-supervised learning, where you're really leveraging unlabeled data only, domain adaptation, which is really relevant, for example, for autonomous vehicles, where you're training under one distribution of data, let's say one particular city or type of weather, and then you're trying to generalize to other ones, and so on. And so this shows some citations and links to some of the great works that have come out here. And my lab at Georgia Tech focuses really on pushing the boundaries of this. And so we've made several contributions in these areas. I should say we are also interested in a lot of the cool stuff that Surtax showed with learning, actual perception and decision making. But right now I'll just be talking about perception side. And so early on, we've worked on various things, such as, for example, discovering new types of object categories. So rather than having the assumption that all the objects that you'll see, and some of the examples that I use here in Atlanta is scooters, where we could train self-driving cars with a few years ago, and then all of a sudden these types of new objects appear. We don't want to have to relabel everything, all the new categories. And so we have some work on how do you discover new object categories. We have some work on few shot learning. So how do you learn with very few examples? And then domain adaptation, especially in the spatio-temporal domain. So that's all stuff that you can check out. Today, I'll really be talking about mostly learning from either unlabeled or semi-supervised, which is a mixture of labeled and unlabeled data. I'll start talking about this work that we have published at ECCV, looking at classification, so image classification problems, and how do we do semi-supervised learning better. But really, the work that has been done thus far really focuses on this type of domain, which isn't as relevant to, for example, autonomous vehicles, where really we want to do other tasks. So, for example, I'll talk about our recent work that's in submission, looking at how do you use very similar principles for object detection, which is obviously a key component of perception for intelligent vehicles, as well as leveraging the fact that autonomous vehicles have many different sensors. And so can we leverage the strengths, for example, of the models that we have for perception in images and somehow transfer them to unlabeled point clouds that we have? Sorry, I'm hearing an echo. Okay, thank you. And so the key kind of thing that I'm going to emphasize is actually the secret to success in leveraging unlabeled data, that is data that you don't have any human annotation for, which is obviously easy to collect, for example, on intelligent vehicles, is actually quite simple. There's very standard things that we've actually known about in deep learning world for a while. It's just we weren't as aggressive about it. So for example, data augmentation, where we perturb our real world data in various ways. What's called pseudo labeling, which means that we take the unlabeled data and we make predictions on them and then basically take the confident ones and feed it back into the training pool, which very simple idea that has existed for decades. And then a little bit more kind of complex methods that I'll talk about, such as graph-based methods that actually model the relationships between pieces of data. And so the kind of, I'll go through some of our methods that actually leverage a lot of these things and some of the keys to them. And then, as I said, I'll move on to things like object detection and 3D, which is much more relevant. So we'll start out with a simple case, which is image classification, just to kind of start things off. And so here, again, in semi-supervised learning, the idea is that you can annotate a small amount of data. So again, in this case, classification, even there, it's a little bit cumbersome to label millions of images. So you're just going to label, let's say, thousands of images rather than millions, typically somewhere in the order of 10 to 100 or 10 to 50 maybe per class. And then we're going to assume that we have a large unlabeled data. And again, I think the cost of obtaining unlabeled data is often much, much less. The example data sets, again, kind of are sort of a little bit toyish with respect to things you see in the autonomous driving, but what you'll see is the algorithms we develop actually are very relevant. And there's been several methods that have come out that have achieved state-of-the-art results here, called mix match and mix up and so on. And the key idea here is, you see in the figures here, is that, for example, we'll take an image of a cat and we'll perturb it in some way. So in this case, you'll see it being rotated. And then what we're going to do is a very simple idea, which is called the consistency loss. That is, we'll feed the image through a neural network to get predictions on both the unrotated and the rotated image. And then we'll have a loss function that says these two predictions should be very similar to each other, because we're not changing the semantic meaning of the data. You can actually have more complex things, such as what's called mix-up, where you're taking here, again, simple toy data sets, image of a 1 and image of a 5, and you're actually mixing in pixel space these images. Seems a little strange, but that's what we'll do. And then we'll actually mix the ground truth labels for them too, or you can also do the predictions for them. And so you're taking the distribution where you have an estimate that it's a 1, another distribution, an estimate it's a 5, and you're combining them. And again, this forms new data that we can feed into the training set. And again, this allows the neural network to interpolate a little better based on the data. So it's moving a little bit beyond the actual data set you have and perturbing it in various ways. And again, we can do a consistency loss. And so this actually has become surprisingly effective for learning with unlabeled data. And this is used in semi-supervised learning, where you have a mix of labeled and unlabeled, or just self-supervised, where you're literally learning effective feature representations using just a large collection of unlabeled data only. And so one of the key things that our work addresses is that this is actually a cool idea, where we're augmenting the images and using them with this consistency loss, but it's really limited in the sense that it's done in image space. So you're performing various perturbations in image space, let's say rotating the image, adding noise, things like that. First of all, this requires a lot of domain knowledge. So we're taking all the image processing knowledge that we have and using that to derive what augmentations we should use. Second of all, if we're trying to apply this to new modalities, we'll have to redo it again, understand what perturbations don't change the semantics of the data itself. And it also doesn't move you out of the labeled data much. Essentially, you can only perturb things so much using these methods because it's hand-coded, hand-designed methods. And so what we've developed is an algorithm called FeatMatch, and this was published recently in ECCV 2020. And so what we're trying to do is we're actually going to try to reason about the relationships between the elements or the pieces of data. And we're going to build what's called the graph neural network that actually takes not just the example image, but also takes what we'll call prototypes. So we'll have a set of canonical examples across all of image classes, and then we'll try to build a graph between the example image that we want to classify and all those other prototypes. And we're going to use a learned similarity metric. I won't talk about that too much, but it's kind of like an attention mechanism where we'll understand or estimate the similarity between this example and the prototypes and try to leverage the features of those prototypes and incorporate them. So graph neural networks basically refine the features. So they take in the features of this example, and by combining it with, for example, in a weighted manner, doing a weighted summation of the features of things that are also close to it or similar to it, it then outputs a new set of features that represent not just the appearance of that example, but also all the nearby things that we know about. And so one of the novel aspects of this paper that we have is that we'll actually view this as an augmentation, but in feature space. Because we're basically feeding in some features for this image and we're outputting new features that combine it with other nearby things in the neighborhood, we'll say that's like a form of feature augmentation, basically. And so then we'll apply a consistency loss, very similar to what we showed before, between the features before the graph, or namely actually predictions from those features, and the features and predictions after the graph. So you see this on the bottom here on this consistency loss. So again, one of the key things we're viewing this as is we're perturbing or augmenting our data in feature space. So this is a much more richer way to perturb the data. Rather than perturbing the pixels themselves, we're perturbing the features that are more abstract or high level. And we'll see that this actually has some cool visualization or interpretability that we can get out of that. So what I mentioned is that we're essentially building a graph between the features and a set of prototypes. And there's a question of how you build these prototypes. What does that mean? And so the way we do this is we actually use k-means, which is a clustering algorithm, very old school standard clustering algorithm. And so one of the key kind of engineering things that make this hard is that you don't want to take all your data. Let's say you have 50,000 unlabeled examples, and you're essentially combined with the labeled examples, and then you apply k-means to it. If you do that every iterations of the optimization, that's going to be super costly. So we have sort of a trick where we're actually going to basically keep the features that we've extracted along the optimization of the deep learning model around, and we're going to store them in memory. And so after an epoch, where an epoch means that we've gone through all our examples to update the model, then we already for free have all the features. They may be a little bit stale because you've updated the weights of the model, and so your feature space is different, but it turns out not to matter much. And so that's how we actually combine the labeled data as well as the unlabeled with their estimated predictions. And then we apply k-means to it, and we get a certain number of prototypes per class. And then we again refine the features of every example using these sets of prototypes. And this shows some of the updation kind of mechanism where we're training the model, and then we extract the features, we feed it through the graph, we apply this consistency loss, and then every epoch or so, we basically take the computed features and then apply k-means again to get new prototypes, and then do this iterative process. So again, one of the key ideas here is that we're doing feature-based augmentation of the data, which moves beyond some of the rotation or pixel augmentation that we have done. So this is using a graph neural network performing feature-based augmentation. So that's one of the key differentiators across all this recent state of the art. And one of the key things is that, again, on lots of these data sets that we have tried, you get a lot of good benefits from this augmentation method. This shows two smaller data sets, SciFar10 and SVHN, which are like digit type data sets. SciFar10 has 10 classes, but is real images. And you could see the error rate here on the bottom that we get for 250 labels and 1,000 labels and 4,000 labels. The full data set is 50,000. And we actually can get really small amount of degradation in performance and error, even with only 250 examples compared to 50,000 examples. So for 10 classes, this is literally 25 examples per class, and that's all we need. We can do larger data sets as well. This is SciFar and what's called mini ImageNet. And again, here the error rates are higher because they're more complex data sets, but you don't see much degradation between, for example, 4,000 and 10,000 examples. And so you can essentially get at least an order of magnitude reduction in the number of labels needed to get very similar performance in terms of classification error. We could try to, so we've also tried this on out of domain data, meaning that what if you have slightly different statistics in your data, and so in your test set, and so we similarly are robust to that compared to the state of the art. And one of the key things, as I mentioned, is this notion that we're augmenting data in feature space, which might provide a much richer set of augmentations. And so if you look here on the left, we're doing normal image-based augmentation. And this is plotting, this is what's called a t-SNE plot that's plotting the features. And so you could see that it's very clumpy, meaning that we're taking the data that we have and we're perturbing a little bit, but using, like pixel color jitter or other types of perturbations, but you're not really moving it much beyond what the actual data is. Whereas if you go on the right, where we're doing feature-based augmentation, you can see it's actually augmenting the data in very complex ways that kind of spans or fills the space much better. So we can also try to understand, like in terms of, as I mentioned, there's an attention mechanism. And what unsurprisingly, we get this block diagonal thing where if we're showing the attention weights on the upper right between the images and the prototypes, and we're sorting them by the classes, you get a block diagonal pattern, meaning that given an image, it tends to find the prototypes of the same class. Again, we don't know that it's what class the image has, but it's using like a learnable attention mechanism or similarity metric, if you will, to try to say which ones are the closest. And it turns out to be the ones that are showing the same class tend to be the closest, which makes sense. And so it's pulling essentially from these prototypes information, feature information to try to augment the data. We don't know what it's doing in the augmentation because it's all in feature space. And what we can do though is find the nearest neighbor in the actual data set. So we can take the perturbed features and try to find what is the closest image in that feature space. And so if you look on the left, you'll see like a bird input image, and you'll see that data augmentation only on the a little bit above it, only that's the augd, only perturbs it a little bit. So it does like various color jitter or other types of perturbations. But what's interesting is that you see the augf, which is the feature-based augmentation, actually perturbs the features in a way that makes it closer to a bird that's in the sky. So again, we're not generating these images, we're just generating the features. But when we do a nearest neighbor to what is the actual data that's closest to those features, it's a bird in the sky. So this gives us some evidence that it's doing much more complex feature space augmentation, which again is why we get much better performance when we have less labels, because it's able to, even though it has much labels, it's estimating the labels on the unlabeled data set and then performing all sorts of complex feature space perturbations to feed it new types of variations that it might encounter, for example, in the test set. So that's the image classification version of semi-supervised learning. But the question is, what about actual things that we care about for intelligent vehicles, such as object detection, 3D data, and so on. And there's been a lot less work on this. And so we have some recent submitted and work on arXiv that is really addressing these much more complex problems. And it turns out that a lot of the principles that I talked about for image classification actually still works. So data augmentation is the key part. pseudo labeling, meaning that we'll estimate predictions on the unlabeled data, and then we'll apply this consistency loss. Still works, but there's a lot of much more complicated things that happen. So for example, object detection has all sorts of complexities that make the algorithm not work when put in vanilla form. And so we have some work that modifies it to actually work on real world object detection data. And so the motivation is clear. We don't want to just classify cats. We want to detect pedestrians, cars, other things in the street. Again, there's only very few works that address this. One thing to note is that object detection is much more complex, right? So if you're familiar with it, there's single stage methods which try to, given an image of a complex scene, output all the bounding boxes of objects all at once. Or there are methods that are what are called two-stage methods that first they estimate regions of interests called ROIs. And then, so that's the RPN, the region prediction network. And so there's a separate branch of the network that only predicts things that might be object-like in the scene. And then given those those bounding boxes or regions of interest, you then classify them and refine the bounding box afterwards. So that's a two-stage method. And so again, this adds a lot of complexity. So rather than just have a convolutional neural network that takes in an image and outputs features and then some predictions, we have this separate branch that outputs these regions of interest. And then there's another branch that classifies and refines the bounding boxes. And there's a set of predictions that are made, typically at least 4 predictions and 4 loss functions that are made. So again, it's just much more complex. And so when we apply some of the vanilla semi-supervised methods to this, some of these complexities get in the way and make it not work well. And so we had several observations analyzing the performance of both the object detectors by themselves under limited amounts of labeled data, as well as applying some of the state-of-the-art semi-supervised methods. So the first observation is that the region proposal network, that is the first stage of the network that actually gives you the candidate regions in an image that might have an object, is actually super important. So we did a test that's kind of like an ablation study where we fed it 100% of the data at the end, which is after you have the region proposals and you're doing classification for them and refining the bounding boxes. But we only used 1% of the data to train the actual region proposal network. That is, the estimates of what might be object-like only gets to see 1% of the labeled data. And what we saw is this results in significant degradation. So you can't just focus on the second stage, which is classifying what's in these regions. The key thing is to make the regions themselves really good and accurate. And again, there's a lot of precision here that you need, because you can't just have bounding boxes that are on half of the object or parts of the object. It has to be relatively precise for the classifier to work. The second observation is that applying a limited amount of labeled data causes overfitting significantly, which isn't surprising. That's a standard thing in machine learning. But essentially, this is true, especially in the first stage of the network. So this is showing the loss function for the foreground background classifier. So again, this is basically just trying to, given a region in the image, is it foreground or is it background? Does it have some chance of having an object in it? And what you see in the loss function on the lower left is that the loss increases the more you train it. And that's a classic kind of evidence of overfitting. And the overfitting also kind of transfers to the second stage classifier, which says, okay, now I know where the regions are that might have objects. Now I'll do a better fine-grained classification of all the classes. And here you also see overfitting. And of course, as you see, as you move from 1% of the labeled data to 100%, you get less and less overfitting, which makes sense, right? This is classical machine learning. But there's a question of why you get overfitting so drastically compared to image classification. And one of the key things that is really important in object detection is imbalance. So the foreground to background ratio is actually pretty horrible, right? So when you actually have ground truth classes or bounding boxes, you know, like the ratios aren't that bad because you know where all the objects are, and you're not considering all sorts of random object boxes across the image. But when you're actually predicting what regions of the image might have an object, most of those are going to be background, meaning you're going to estimate that there might be an object here, but it's like patches of grass that kind of look object-like for whatever reason, for example. So there's a whole kind of large imbalance, and so the key overfitting aspect really relates to this imbalance, which is the foreground-background classification, which is the part that has the most severe overfitting. And so we looked at this and said, well, you know, these are pretty hard challenges. And so the first question that you might ask is just, can we take the same idea as what we did before, which is apply some of these semi-supervised learning methods? And I should say FeatMatch is one of the key methods that's state of the art that uses this consistency loss that I talked about, and apply it to object detection. So what we did is essentially applied it to here the ROI head, meaning that we're essentially doing pseudo labeling. So here a particular image gets augmented in two ways. It gets augmented in a weak way. So you're not applying a lot of augmentation, but you're doing something like flipping or maybe tiny amounts of perturbation of the pixels. And then you make predictions, both the RPN region prediction network, and then it predicts bounding boxes, and then you make classification predictions on those. And so that's the teacher network that gets fed, that makes predictions in terms of pseudo labeling. And then those predictions are then used as ground truth, pseudo ground truth, to train another branch where you're applying much heavier augmentation. So these are what's called strong augmentations. So these, as you can see, it's kind of depicted here, you know, has much stronger types of perturbations. And of course, we can combine it with our feature space perturbation idea. We haven't done that yet. And then, you know, we're essentially training this model where we make predictions, and then those predictions have to be consistent with the pseudo labels that we got from the weak augmentation. And so this is very similar to the FeatMatch algorithm that's applied for image classification. Um, but it doesn't actually work. So when we only use 1% of the data, if you only do supervised learning, which doesn't perform that well because it's not seeing a lot of data, it actually FeatMatch doesn't do well at all. It actually gets worse than supervised. And so the reason is that all of these different factors that I talked about, the foreground background imbalance, the overfitting issue, gets really propagated through the pseudo labeling process. So if you think about it, if your predictions on the weak augmented data isn't very good and you're using that as ground truth to train the strongly augmented data, it's going to have like a negative feedback loop. And here the imbalance is going to get worse and worse, because essentially what you'll have is different foreground background ratios at different parts here. And then your pseudo labeling itself will have large imbalances. And then when you feed that in to train the student network, then that imbalance is going to propagate. And this propagates to the what we call pseudo label bias, meaning that essentially it'll be very biased towards the background class. So all your estimates will be background class, and then that gets trained, used to train the student network. And so, yeah, this kind of pseudo labeling, you know, iterative process just breaks down if you apply it in the naive way. So that will lead to this empirical performance that we saw, which is that it's worse than even just supervised learning. So we have a method that addresses a lot of these issues. I can't, due to time, get into all of these aspects, but we use several different methods to address the key challenges. So the first thing is we also use something called a focal loss, which is a loss function that's much more robust to imbalance. We also use what we call EMA, or actually is commonly called as EMA, exponential moving average network, where we have a teacher network that's not just essentially the actual network itself, but it's averaged over the iterations to make it a much smoother teacher for the student. And so we kind of have two phases here. First, we just do student learning, meaning that we just learn from the labeled data combined with the estimates from a frozen teacher network. And then we also have a stage two where you're refining the teacher itself through this exponential moving average. So I know it's quickly, I went through this quickly, but and there's a lot of details here. This is in submission, so we don't have a lot of details out yet. But what we can see is that we can actually get much better performance across different amounts of labeled data. So this is on the COCO data set for object detection, and we use 1% of the data labels, 2% of the labels, 5% of the labels, and 10% of the labels. And then we also use, we can use the rest of the unlabeled data as unlabeled data for this consistency pseudo labeling loss, as well as COCO actually has also, I mean, there's other aspects of the data set that's not labeled that we can use. But if we only use one label, 1% of the labels, this is just this normal supervised learning method, you can see it degrades all the way from 23% all the way down to 9%. This is a mean average precision where you're kind of averaging the performance across all the classes. I think 100% of the labels is somewhere around 35 or upper 30s. We can see that there's a state-of-the-art method from Google that's, I don't know if it's been published, but it's out on archive, that gets significantly better. But if we apply our understanding of unique challenges in object detection, we can actually do a lot better with our method. And so what's cool is you could see that, you get kind of like a twofold decrease in the amount of labeled data that's needed with our method compared to the state of the art, and maybe like a 4 or 5-fold decrease in amount of labeled data needed for compared to just the normal supervised baseline. And if you kind of move on to higher labeled regimes, you see this trend as well. So we can get, again, like a 4 to 5-fold decrease in the amount of labeled data. And we're continuing to push these boundaries to try to even do it better. I think in the image classification case, as I mentioned, right now we can get 100 fold decrease sometimes from 50,000 labels to just like 500 or 250. We're not there yet for object detection because it's much more complex and a harder task, but we're really getting close to pushing these boundaries. So that's kind of the methods that we have developed for object detection. So again, semi-supervised learning for object detection. In intelligent vehicles, we often have LiDAR, which is 3D sensors. And so there's a question of how do we do this for 3D? So 3D, again, is a much harder task. So I think image classification is the easiest, object detection is kind of next, and then 3D is even harder because you have unstructured point clouds where you're kind of losing a lot of the elements that convolutional neural networks are good at. And in the past few years, people have developed really good neural network architectures for addressing these, but it's not quite there yet. And so, the 3D object detection goal is to actually get these 3D bounding boxes that are amodal. That is, you get the full spatial extent of the data. So in LiDAR and images, you only see parts of the data. And so you really want like a full 3D bounding box on top of all of these things. And so there's a question of whether we can leverage the success of object detection and semantic segmentation, that is pixel-wise classification per object instance, into the images. So often in intelligent vehicles, we have all of this data, right? We have both cameras, typically many cameras across different viewing angles, and then we also have LiDAR, and we can register those two sensors, right? Spatially register them so we can project the pixels in the image onto the LiDAR, or we can project the LiDAR points onto the image. And so we've done some work. This is work with Argo AI, Ben Wilson and James Hayes at Georgia Tech /Argo AI. And we have an archive paper on this to actually leverage, if we don't have labeled data in the 3D point clouds space, can we leverage just the normal, COCO and other data sets that we have that are of street scenes and their success in object detection and semantic segmentation, and somehow feed that or pipe that into the 3D realm. And so this turns out to be actually relatively easily doable. So what we can do is, there's lots of works that have had similar ideas, not quite in this unsupervised realm that I'll show, but even in the supervised realm where you're trying to combine images and LiDAR. There's been lots of works where you can do the geometric obvious thing, which is, again, take the images, take the frustum kind of viewpoint that the camera projects to, and just project it onto the point cloud. And you can do the vice versa as well in the reverse fashion. And so we can take an image, we can apply a normal semantic segmentation algorithm or instance segmentation algorithm, where it gives us essentially an index and a class or category estimate for each point here. And we'll take those pixels and project them or colorize the point clouds. So colorize the points that hit those pixels. That's an easy geometric thing to do. And so what we're gonna do is we're gonna take all the LiDAR points in the particular instance segmentation, frustum, and we're gonna actually leverage another piece of data that we have, which is maps. So all of the self-driving car companies have, and make use of high definition map information. And what we're specifically going to use is lane information. So what we have are what's called center lanes, which are essentially, you have these kind of geometric descriptions of where the lanes are and what directions they go. And so what we're going to do is we're going to use this to improve the orientation estimates. So specifically, we'll take this segments that we get, we're going to project them onto the LiDAR, and we're also going to fix the orientations of these objects. So sometimes if you estimate just the orientation from the actual 3D points that you get that are hitting these segments, then you might get either reverse orientations because you don't know which way the car is going, or other kind of mistakes in the orientation estimate, as well as you only get a partial bounding box. So we're going to use the map data to improve the orientation estimate using the center lines. We're going to assume that the objects such as cars go along with the center lines. Hopefully nobody's going in the opposite direction of the lane. And then we're also going to do what's called amodalization, which is also expand the bounding box based on known sort of or estimates of our objects. So we can kind of know extents of average car lengths and things like that to do that. So these two things in combination really improve our estimates of the bounding box and their orientation. So now what we've done is, again, we've taken a segmentation in an image space, we've projected it onto the points in the point clouds. Now we have some segments or points in the point cloud that reference this particular object. And then we'll fix the orientation using map data. And then we'll also enlarge the bounding boxes to make sure that we get the entire object. And again, this is kind of, we can do this for any arbitrary images, just, get these estimates. And, what we're really relying on is that we have really good image segmentation data sets for street scenes like Coco and lots of other ones. And we're going to leverage the fact that they give you pretty good segments in order to project them, or in what we call inflate them into 3D. And so again, we're going to project them onto the points. We're going to get really good 3D bounding boxes. And if you've noticed, we got this for free. So there's nothing in the 3D point cloud data that we needed to annotate. So now literally you can drive your car augmented with the sensors, gather tons and tons of 3D data, and register it with the images and get free bounding boxes essentially for this 3D data. And we'll do this for all the objects. And so you can actually measure the performance of just this simple procedure. We haven't done any machine learning yet. We've literally just we've done machine learning when we applied the segmentation algorithm to the images, but we haven't done any 3D machine learning here. And so we use no annotation in 3D space specifically. And so we can compare how well this does to a supervised baseline. So here, a supervised baseline is from this citation up here. So essentially what we do is essentially, yeah, just like we do actually have labeled data in the Argo verse data set. And so we use those labels to train a supervised model. We throw away those labels and apply our method without the labels and see how well they compare. And if you look, it's actually really good. So we get actually slightly better mean average precision, again, using no learning except for image segmentation, no learning on 3D, no human annotation on the 3D data. And we also have a bunch of different metrics. So we have translation error, which is MATE. We have the scaling error and orientation error. So you can, and CDS kind of combines these in a linear equation, just to get one number that combines translation, orientation, and scaling errors, and mean average precision. And again, we're really close to supervised baseline with no 3D data that's been annotated. One of the cool things is you can gather balanced data. So again, if you're annotating, typically you get very large imbalances because you can only annotate so much data, and you only have so many examples of things like motorcycles or pedestrians, or specific types of buses, things like that. But if you're just
We have
gathering, you're mining.
two
Sorry.
minutes.
2 minutes? Okay, sure. I'll speed up. Yep. So if you're gathering, this just in an unsupervised way, then you can just keep gathering to your heart's content and really have a lot more data for these rare objects. And then you can actually train on this. So we'll apply the pseudo labeling idea to basically just take these 3D bounding boxes that we estimated and just use them as ground truth, even though they're noisy, and train on that. And then we can even further improve the mean average precision. And what's cool is if you look at the rare objects like things like bicycles and motorcycles, we get actually much better results than the supervised baseline just because they're very imbalanced. And so the idea of gathering a large scale unlabeled data set that you can leverage 2D computer vision to annotate in a pseudo labeling kind of way really makes up for this imbalance issue and allows us to do better than supervised. And this is scalable. So we haven't actually scaled this to beyond 10 to 10 cubed unlabeled trajectories. So these are trajectories, but we can continue to do it to our heart's content. I'm sure it'll plateau at some point, but we haven't reached that plateau yet, and we're better than supervised just because we're limited in how much supervised data we can have. One of the key last points I will say is all of this stuff is very underutilized. So we've shown an example where we have 2D and 3D, and we can leverage the good computer vision algorithms that we have trained to like inflate to 3D. But in reality, we have all sorts of other data, right? We have positioning data, we have depth sensing, stereo, other things. And this taxonomy kind of paper from CVPR shows us that there's a relationship between all these different tasks. And so I think the notion of using all of these cross-modal information in especially self-supervised or cross-supervised manner, I think is a very rich space that we haven't really pushed the boundaries of. And I think especially for intelligent vehicles, we can really improve our performance such that we don't need to gather a whole ton of data for everything. I'm going to conclude since I'm running out of time, but I'd like to thank the PhD students who do all of the work. This is in collaboration with organizations such as Facebook and Argo AI, and funded by various organizations, NSF, Samsung, and DARPA. So with that, I'd like to thank you, and I will be happy to take questions.
So I think you can only hear me clap. I think everybody else is clapping in front of their own cameras. Thank you very much. Questions. If you have questions, you can post them again in the chat or use the raise hand or maybe speak up. I know it's a bit hard to do interactivity in this online setup. And maybe, I also don't think we have a lot of time for the questions. We're just before the break. Maybe I will sort of kick off with a question. And what I find interesting is, if I think about sort of the classical methods, also in semi-supervised learning, where you have these graphical models, and for example, you do a mixture of Gaussians, there's also this idea that you don't want to make hard assignments, right? You might be uncertain about, is it be part of this object or this class?
Right.
And that's, if you think about the EM algorithm, by iteratively updating it after a while, you might not be forced to include some object into a clause where it might mess up
Right.
your predictions. So in the experiments that you showed, in the ideas that you showed here, where you had that pseudo labeling, was this like a hard labeling or is it soft labeling? And is there any space for modeling uncertainty about the labeling, or are you using that idea?
So semi-supervised learning and self-supervised learning are kind of intersecting fields that are starting to compare and contrast. And I think all of the above are true. So the methods that I showed for semi-supervised learning are hard pseudo labeling methods where you're I mean there's a threshold, so we're only taking confident predictions. So you're really relying on the thresholding to remove things that are not good, and only taking relatively clean data. Um, as I showed for object detection, that really matters, right? Like if you have imbalance or other issues, that can throw your pseudo labeling off as well. So far as semi-supervised learning, because you're typically leveraging unlabeled data with the same categories, the hard pseudo labeling approach works really well. For self-supervised learning, or where you're applying things to outer distribution data, so for example, if you have labeled data in one distribution and unlabeled data in other distributions, what we found is that actually a combination of both of these losses work. So you can also have soft pseudo labeling, which means that you either have the distribution of data, or even you can have losses that match features rather than probabilistic predictions on the classes. And there's a lot of self-supervised learning methods that are doing this. So there's something called Bring Your Own Learning, which actually does this. It has a teacher-student model, and it's doing a soft pseudo labeling sort of approach. So it's called, yeah, kind of consistency losses, but soft in a soft way across features, not probabilities. Um, and what we find is actually, and something that a lot of papers, in the past few weeks actually are coming out, is that the combination of these two is the best, because you don't know whether data is going to be out of distribution or not. And so, when it's not out of distribution, when you have enough overlap between the unlabeled and labeled, for example, then hard pseudo labeling gives you much stronger information if it can be accurately done. On the other hand, if it's out of distribution, then it won't work as well. The pseudo labeling, the threshold will throw away a lot of stuff. And so the combination is actually what works the best, I think. And that's something that's going to come out in the next few months or a year. Yeah.
Great, thanks. Thanks a lot for your answer.
Yep.
Any last questions, maybe on the chat or from others? I think, yeah, we're also at the time of the break. I'm not seeing anybody raising their hands now. So yeah, great. Thanks a lot. Let's thank the speaker again.
Thank you very much.